Math 287, Cuesta College. I'm Joe Vasta, and we are going to cover section 4.4, which is called spanning sets. So the first thing that I'd like to point out, maybe I'll write it down here, is for you to do the homework in the specified order that I listed on the homework sheet. So in the specified order. Okay, let's go ahead and look at some definitions, because it looks like I have a problem and it says write U as a linear combination. So what is up with linear combination? We'll take a look at this right now. So spanning sets. Let V be a vector space. S is a collection of vectors in that vector space. There's K of them. It's a subset of V, not to be confused with subspace, so it's a subset. And the CIs are scalars. U is a linear combination of the VIs if and only if U can be written as scalar times V1 plus scalar times V2 plus yada 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 plus scalar times VK. So forming all linear combinations of the VIs generates a subset of V called the linear span of the VIs, denoted by the word span V1, V2, yada yada yada, VK, or span S, since S was that. So I know these are very technical, and the only way we'll get comfortable with them is by doing examples, and you'll get truly comfortable with these when you do your homework. So let's go ahead and take a look at this question here. You have two vectors in R3, okay, V1 and V2. And they're asking you, this third vector, 4, 2, 0, does that lie in the span of V1 and V2? If yes, write U as a linear combination of V1 and V2. Okay, so to check to see if this lies in the span, it's new vocabulary, so that it does feel weird. You try to see if you can write this vector as a linear combination of V1 and V2. Now, how do you do that? You put a scalar here, C1, negative 1, 0, 1, plus C2, 0, 1, 2. So can you find two constants where this will be true? And that's what we're going to do. So notice what I have. I can set 4 equal to the sum of the first two elements here in each of those vectors. So that's what I'm going to do. I'm going to say that 4 equals, okay, so I pick up the first element there, or the first component, negative C1 plus 0. I'll write that out even though I normally wouldn't. 0C2. So that's how I got that first equation, the first components. The second components will give me 2 equals 0C1 plus C2. And the third components look like this. 0 equals C1 plus 2C2. Okay, so there it is. I'm seeing if I can find constants that will work and make this equation true. So look at that first equation. That first equation I could already solve for C1. C1 equals negative 4. And the second equation we can solve for C2. It's already done, really. This is C2 equals 2. Now, I've got to make sure that that works in the third equation. So let's see if it does. I have 0 equals C1, which is -4, plus 2 times 2. So this is 0 equals -4 plus 4. And that does work, which means the answer is yes. Okay. Now, if this had looked different, like perhaps what if there was a 3 right there, then there would have been a 3 there, and this would not have worked, then the answer would have been no. So yes, U does lie in the span of these guys. This is the span of those guys. If yes, write U as a linear combination of V1 and V2. Well, let's take a look at this. This guy right here is -4. C2 is 2. I mean, you can double check to see that it does work. Look, it says 4 equals 4. Yeah, and then 2 equals 0 plus 2. 2 equals 2, and then 0 equals -4 plus 4. So it does work. So I'm going to go ahead and write U as a linear combination. I mean, there it is right there, but I'm going to make it a little more compact. I'm going to say that U, which is this guy here, equals, I'm just writing this equation again, -4 V1 plus 2 V2. So I finished this problem. Okay, our next problem is going to ask us to do some more things. So we're trying to get used to this concept of linear combination. We just wrote this vector here, 4, 2, 0, as a linear combination of the other two vectors. We'll just put this like this. Let V1, okay, so we have the same V1 and V2 as the original problem. Let me just do that there. And then they're asking me to find the span of V1, V2. Okay, so what is the span of that? Let's go ahead and do some relabeling before I do this. Let's call V1, V2, let's just call this set S. And then we'll call this the span of S. This is the span of S. We'll call that T. Okay? So when they say find span of that, they're really saying find span of S. And if you look back at the definition, it says forming all possible linear combinations of V1 and V2 generates a subset of V called the linear span, or you can denote it with span S. So what is this guy right here? This guy is that. So let's write that out. Span of S equals this. -4 times -1, 0, 1 plus 2. And then we have 0, 1, 2. So I'm going to go ahead and write this as one vector. And actually, what I did was wrong. The span is what I circled in yellow, but it's all possible linear combinations. This is just one linear combination, so I really should have kept the C1 and C2 in there. There we are. Let's get rid of that there. So this is C1, C2. So that's what the span is. That's all possible. When I had the -4 and the 2 there, that was just one linear combination. Notice that this says forming all possible linear combinations of V1 and V2 generates the linear span. So this is also called the linear span. I'm going to write this in terms of one vector here. So -C1, comma, the next one is C2, comma, and then this is C1 plus 2C2. Okay, and that's kind of like what we have over here on this side. So what am I going to do? So this is the span. Let's write out our answer officially. Span of S is, and we're going to use the set builder notation, the set of all ordered triples that look like this. -C1, comma, C2, comma, C1 plus 2C2, such that C1 and C2 are elements of the real numbers. So there it is. And so I was referring to this span S as set T. Okay, so we could say T equals that. Now this is going to help us a little because set S is right up here. Let me just write out set S. Set S happens to be V1 and V2. How many vectors are there in set S? Well, set S has 2 vectors. Now here's the span of S. We can cover that up now, which I'm calling set T. Set T has how many vectors? Well, looks like infinitely many. Many vectors. So what I'm going to do is I'm going to call set S the seeds. These are the seeds that generate set T, all these vectors here. So what is set T? It has infinitely many vectors. This is a plane. These vectors all lie on a plane in R3 going through the origin. In fact, you can find the equation of the plane by doing a cross product of these two vectors. And I think the plane is like x minus 2y plus z equals 0. That plane in R3 is a subspace of R3. Okay, so this right here is a plane in R3. Let me just write that down. This is a plane in R3, which is a subspace of R3. So I think it's time we look at some definitions here. Span S, so this is a theorem actually, is a subspace of V. So anytime you take all linear combinations of some vectors, and we did all linear combination of 2 vectors, you get a subspace. If span S equals T, kind of like what we have in our example, that's why I chose those letters, then S is a spanning set of T. So the set of seeds happens to be, this guy right here, is a spanning set. Okay, and we can say of T if you want, but it's a spanning set, and that's what 4.4 was called, spanning sets. We can say S spans T Okay. Or T, which was that plane, is spanned by S. That's why I call S, the spanning set, the set of seeds, because the seeds generate the span. They generate, in this case, the plane. Okay, so that was definition. So let me go ahead and say these are the seeds used to generate all these vectors. And how do we generate them? We do linear combinations. We mix a little of this with a little of that. You know, we could do 2 parts of this plus 5 parts of that, and that gets me a vector that is in the span. We can do -7 parts of that and 20 parts of that. That gives me another linear combination, another vector that's in this span. Let's go look at sort of an unconventional example of this. We're going to do a lot more examples of this. So if you're kind of like going, wow, I'm really confused. Well, here's something that will confuse you maybe more. Look at this. S is a set of vectors. Red and yellow. Okay? So you're like, these are vectors? Well, remember, the 3 stooges could be vectors if we define things correctly. So let's just say we have a vector space where vectors are colors, and we have a set of seeds. There's just 2 of them there. T is the span of red and yellow. Okay, maybe we're not going to make scalars be negative numbers or whatever, but anyway, we have the span where we do all mixtures of red and yellow. So we can, first of all, ask, how many elements are in S? Well, S contains 2 elements, or 2 vectors. What about T? How many vectors does T contain? T contains, well, how many different ways can you mix red and yellow? We can do 3 parts of red with 2 parts of yellow. There's infinitely many ways you can mix those. So T contains, and I'll shorten this up, infinitely, there's an ly there, infinitely many vectors. Or maybe I should have said elements, because I said elements there. So let's ask these questions here. Does orange lie in T, which is the span? Can you mix red and yellow together and get orange? And the answer is yes. Does green lie in the span in T? So can you mix red and yellow together and somehow get green? And the answer is no, because we are missing something in here. Aren't we missing the color blue? So you cannot get all colors just using red and yellow. The answer is no. Now, if you're not very good with colors, then forget about this example. But I'm using it as an analogy because take a look at this one right here. The span of these 2 vectors, this is like red, this is like yellow, and these are all the colors you can make from red and yellow, which happens to be what? A plane. But it doesn't give you all of R3, it just gives you a slice of R3. Just like red and yellow give you not all of the colors, but just a slice of the colors. You know, different shades of orange and red and yellow, but it doesn't give you things like green. So let's continue, remembering that a spanning set is the set of seeds. So this right here is the spanning set. And this right here is the span. This is everything that you can generate with these seeds. And somehow this is very important in linear algebra. Let's go do some more kinds of examples that you'll see in your homework. We're going to go ahead and look at example number 4. Let P be x squared minus 2 and Q be x plus 1. So those are 2 vectors, and we can say those vectors are, the vector spaces maybe P, 2, which is polynomials of degree 2 or less, but we don't have to say that to do this problem. Does f, which is x squared plus x plus 5, does that lie in the span of p and q? So this is just like problem number 1, except the vectors are not R3 anymore, they are polynomials. If yes, write f as a linear combination of p and q. So how do I start this? I start it like this. I write x squared plus x plus 5. And it asks, does it lie in the span? What is the span of these guys? Well, the span is all linear combinations of p and q. How do I write linear combinations? Constant times p plus constant times q. So there it is. Can we find a C1 and a C2 where this will work and we'll be happy? If we did, then this is kind of like orange, and that's like red and yellow. If we cannot find a C1 and C2 where this works, then this is like the color green. And say, no, we cannot come up with this polynomial using these two colors, or these two vectors. So how am I going to do this? I'm going to go ahead and use the distributive property on the right hand side 2 times. So this is c1x squared minus 2c1 plus c2x plus c2. Okay, so now what I'm going to do is I'm going to go ahead and circle all my constants. Okay? So here's a constant here, which is 5. And what else do we have? We have a constant. Now, you're thinking that's not a constant, it has a C1, but it doesn't have an x. Okay, so circle all the things that do not have x's. And so that gives us an equation that says 5 equals negative 2c1 plus c2. So this is the green equation. Let's go ahead and circle all the terms that have x's in them. So here's an x, and here's an x right here. Now, it's true that the coefficient in front of this x here has to equal the coefficient in front of that x. This probably reminds some of you of partial fraction decomposition. So instead of saying x equals c2x, I'm going to say that 1 equals c2. I'll put a little red dot there. And then the last thing I'm going to do is I'm going to circle all my x squared terms. So here's an x squared term. There's an x squared term. And those coefficients have to be the same, so look at this. 1 equals c1. And I'll put a little blue dot right there. And so this is just like the last problem. Remember, or not the last problem, but this problem where we had 3 equations and 2 unknowns. And we were seeing if we can get something that works for C1 and C2. That's exactly what we're doing here. In fact, notice this. Those guys are already solved for. C1 is 1, C2 is 1. So let's see if this works. 5 equals negative 2 plus 1. No, it doesn't work. Wow. So we cannot find a C1 and a C2 where this will work. So the answer is no. Does F lie in the span? The answer is no. F does not lie in the span. There's no way you can write that as a linear combination of those. F, with our analogy, we can say F is, well, no, I've ruined our analogy because I've used green, but F is like the color green, and this is like red, and this is like yellow. And so you cannot create green from red and yellow, and we just showed that. The answer is no. We're done with this problem, but before we leave this problem, you could have, if you were extra weird or whatever, you could have said, oh, there's 3 equations, 3 unknowns, and you could have written an augmented matrix. I wouldn't have done that, but I mean, let's just do that right now, just show you that if it does get complicated, then augmented matrix is something you can do. So the next one would be this one right here, and then the last one would be 1, 0, 1. I gotta be careful because the 5, 1, 1 is the right-hand side vector and it's on the left-hand side there. And then this is C1, C2. And you could have said, oh, let's go ahead and solve this. I went ahead and did it, you know, I did all the work already. So what I reduced this to was something that looked like this. And then the last one became 0, 0, 1. Okay, so you can you can do that if you want. Put it in row echelon form or reduced row echelon form. But look at that last equation. So this is C1 and C2. The last equation says 0 equals 1. So anytime, even on problem number 1, I could have thrown those 3 equations and 3 unknowns. Oh no, it was 3 equations, 2 unknowns. I could have thrown them into an augmented matrix and I would have ended up getting the same results. Okay, I say that because there are some times where it's not this simple. Look at this. This is pretty simple to solve, but when it's more complicated, the augmented matrix will always work. So that is the deal with problem number 4. But you know problem number 5, if I'm anything like I was with problem 1 and 2, this is problem number 5. So we're done with this. The answer is no. F is not in the span. So here we have it again. We have P is x squared minus 2 and Q is x plus 1. Find the span. And so the span is right there. So let's go ahead and write that out. Now, how am I going to write this out? I want to write this out as an element, as one vector. So I'm going to, I actually did it right here. I multiplied it all out. So I'm going to say the span happens to be that yellow part, which is C1 x squared minus 2C1 plus C2 x plus C2. Now when we write out polynomials, you know, and we're talking about the vector space P2, we like to write them out like either in ascending order or descending order. So that's what I'm going to do. I'm going to write C1 x squared, then I'm going to put the x next. So I'm going to say plus C2x. All I'm doing is changing the order around, and then I have plus negative 2C1 plus C2. So there's a polynomial. It looks like it's in the form ax squared plus bx plus c. Now, do you really need to put parentheses around that? No, we don't have to, but I'm showing you that it looks like a nice vector now. And so our span, because they're asking us to find span, and you know, we can say that this is really T, is the set of all those animals such that C1 and C2 are elements of the real numbers. And so we have just found the span, and that's kind of like what number 2 looks like. See, number 2, we had the span, we wrote it in the set notation, except those are elements in R3, and these are elements in P2, which is polynomials of degree 2 or less. So there's a polynomial right there. Okay, and we could ask the same questions. How many elements are there in just S? And I can call this S right here. Well, obviously you can count them. There's 2 of them. And then how many elements are in span of S, which is T? There's infinitely many polynomials. There's lots of different colors we can make with those 2 polynomials. So that completes problem number 5. Let's go ahead and do problem number 6. And maybe with problem number 6, you want to see if you can do this one on your own. So let me go ahead and put this up right here. Okay, what do we have here? So let's label some things. A1, A2, A3, those are the seeds. So I'm going to go ahead and circle this. I'm going to call them the seeds. S. And remember, the set of seeds, that's called a spanning set. Okay, so we're going to span it. So it's asking, so this is just like problem number 1, just like problem number 4, where it gives you another vector. These are vectors in M2. It gives you another vector, and it asks, does it lie in the span of those 3 vectors? So what you do is you take this vector B, which is a matrix, and you write it out. 4, -3, -7, 5. And it asks, does that lie in the span of those? So what is the span of those? Writing all linear combinations of A1, A2, and A3. So I'm going to go constant times A1 plus constant times A2 plus constant times A3. So this is actually going to generate 4 equations with the 3 unknowns C1, C2, C3. So I'm going to write out those 4 equations. 4 equals C1. So what I'm doing is I'm collecting the top left element of each of these matrices. So plus 2C2 plus 0C3. Okay, now the top right entry would be -3 equals 3C1 plus C2 plus 5C3. Okay, bottom left, -7 equals 2C1. I corrected that one there. Minus C2 plus 5C3. And then the last one's going to be 5 equals 2C1. No, I was just kidding. Wasn't a funny joke. Let me, what's happening to my, am I doing this wrong? Oh, it just broke. Nice. Oh, I ran out. Oops. Okay, so it broke. Okay. Oh, there's all those plastic parts lying there. Okay, so we do the next best thing. Okay, that was before they had whiteout. They did that. Okay, 5 equals -C1 plus C2 minus 3C3. I don't have any other whiteout that I see here. I'm looking around, so I better not make any more mistakes, because look at that, that looks bad. So this looks really complicated, and what I'm going to do is I'm going to throw this excuse me, into an augmented matrix. Making sure that this guy right here, that's my right hand side vector. So the first row is going to be 1, 2, 0, 4. Do you see how I got that? 1, 2, 0, and then I put 4 on the right hand side. The next one's going to be 3, 1, 5, -3. And then the next one is going to be 2, -1, 5, -7, and then the last one's going to be -1, 1, there's a 1 there, -3, and 5. There's the equal sign. This represents C1, this represents C2, this represents C3. Okay, we're going to stop right here before we continue. I just smeared it there. And I want to point out something. And these are things we could have pointed out before. Let's see. Yeah, they were. Okay. So watch this. See this matrix here? Look at the first column. It says 1, 3, 2, negative 1. Where do we see that? Right here. 1, 3, 2, negative 1. Look at the next column. That represents that vector. And the last column represents this vector here, this matrix. And then of this last column, well, here's the right-hand side vector, which represents the one in question. And when I went ahead and did this on problem number 4, look at our first vector. It's x squared minus 2, but it's kind of like 1x squared plus 0x minus 2, or if we did it the other way, negative 2 plus 0x plus x squared. And then this one is 1 plus x plus 0x squared. So these columns here kind of represent these vectors. And then this one right here is 5 plus x squared. Okay. Now some of you are like, oh, so maybe I should just jump to the augmented matrix right away. Well, you don't want to skip too many steps, especially if you're new with this. So it's good to write down the steps. And what would you do with this augmented matrix then? Looks like what you would do is you would do a lot of row operations. So I'm going to do the row operations for you, so you don't have to sit through 10 minutes of me doing row operations. So this matrix here, which we'll call this A augmented. I'm going to go ahead and do the row operations for you, and when I did them, I ended up getting 1, 2, 0, 4, and that's no big surprise because that's the first row. And then, I did some operations. You could verify to see if I got this right. 0, 1, negative 0, 1, negative 1. This is the lecture without whiteout. Okay, well, negative. You know what? I'm going to turn off the video and go get some whiteout. Okay, I ran and got some whiteout here. Okay. Oh, look at that. I'll try not to throw this one against the wall. The other one's still lying in pieces. I didn't think I threw it that hard, but oh well. What are you going to do? What am I doing? Oh yeah, so I went ahead and I reduced this matrix. And you should even be more suspicious of me because, what's the deal with the whiteout, the anger management? What's happening with this guy? Well, there's the matrix. So I went ahead and row reduced this one. So it said this. Here's the equal sign. Here's C1, C2, C3. And I don't have an instance where I see like 0 equals 1, so it looks like I'm going to have a solution. But look at this. Looks like one of my variables is going to be free. This is bound, free. So C3 is T. The second equation tells me that C2 minus C3, so minus T, equals 3. So C2 equals T plus 3. Now the first equation, and let me circle the important results here. The first equation gives me C1 plus 2C2, so C2 is T plus 3. This gives me 4. C1 plus 2T plus 6 equals 4. So C1 gives me what? Negative 2T, and then we subtract there, minus 2. So let's get back to this question here. We've got our vectors, And it asks, does B lie in the span? Well, look, we are able to find a solution to this. In fact, we didn't just find one solution, we found infinitely many ways that we can create this matrix by mixing these guys together using linear combinations. So what I would suggest you do, because they say, okay, does it lie in the span? We're going to say yes, it does. If yes, write as a linear combination. Well, how do we do that when there's infinitely many different ones? You just pick one. So you pick a t value. Let t equal whatever you want it to be. I'm going to let it equal 1. So if I let t equal 1, looks like C1 then is what? C1 is -4. C2, I'm going to move this up so I have more room here because I'm really looking at this guy right here. C2 is 4, and C3, if t is 1, is 1. So look at this. Let's circle these guys right here. These guys go right here. There, there, and there. I mean, so you could put a -4 there, 4 there, and a 1 there. And so I'm going to go ahead and write out my answer. It says, you know, if the answer is yes, write B as a linear combination. So watch this. B equals, so there's B. I'm just writing this equation down, but I'm lazy, so look what I'm going to do. B equals -4 times this guy, which was A1, plus 4, I'm writing this down, this is A2, plus 1, A3, and I'm not going to write the 1 there. So there's the answer. So we have the answer. This is great. There's infinitely many solutions. Now some of you may have noticed that you wanted to let t equal a different value, like t equals 0. Well, if t equals 0, so we're done with the problem, by the way. I'm just having a math nerd moment. So C1 would then equal -2, and C2 equals 3, and C3 equals 0. So I could have, so this is my answer, but I could have instead said B equals, watch this, I'll circle this in purple. So we could have had a -2 here instead, a 3 there, and a 0. And you can check this out. I mean, look at the first thing. It says -2 times 1 plus 3 times 2. So that's 6 minus 2, which is 4. And then, you know, you can do that. So we have, what is this? This is -2A1 plus 3A2. And then you don't need to write this, but plus 0A3. So that's another answer you could give. There's infinitely many answers you can give. So here is the thing. There's a deal with this. This is like having the colors. Okay, so let's take a look at our colors. This is like having colors red, yellow, and orange. Where this guy here is really not needed to get what these guys can get. Do you see that? So look, B equals this. We didn't need A3. And so we're going to talk about this in the next few sections, but like A3, I'm going to introduce you to a term that is not in your book, is dead weight. It's in the pack of seeds, but it's not a contributor. It could be, look, like on this one, it looked like it was a contributor. But all it is orange, and when you have red and yellow, you don't really need orange to make mixtures that, you know, like this one. This one was like probably a shade of orange, and we could have just used the first two colors like we did right there, see? So dead weight is going to be very important when we talk about linear independence, linear dependence, and that's not in this section. The important thing was, can we answer this question? Does B lie in the span? And if it does, can you write B as a linear combination? And we did. You know what the next question is going to ask. The next question is going to give you the same vectors, which are elements of M2, 2 by 2 matrices, and they're going to say find the span of those. So this right here is really that right there. The span is the set of all linear combinations. Is what I have circled in orange. The only thing we want to do is we want to use the set notation, and we want to write that. Is that orange or yellow? I think it's yellow. The only thing that we want to do is write this all as 1 2 by 2 matrix. Can we write this all as 1 2 by 2 matrix? Well, the answer is yeah, I think we can. So let's try not to get off the range here, of the camera range. And so I'm going to go like this. So I'm just going to say this is C1 plus 2C2, and then there's a 0 there. So C1 plus 2C2. And then the top right is 3C1 plus C2 plus 5C3. Okay, bottom left, 2C1 minus C2 plus 5C3. Bottom right would be negative C1 plus C2 minus 3C3. And so that is what it looks like. Let's put it in set builder notation. We've been calling these spans, I've been calling them T, but you can say span S if you want, because remember that's S. Can we even see that up there? That right there is S. But we'll just go ahead and finish this off here. So this is the set of all of these creatures here, such that C1, C2, C3 are elements of the real numbers. Let's make this brace be really big so it matches that one there. And now I'm going to box this answer. There it is though. And we have it. Now I would want to point this out here, this thing that I see. You know how we had C1 plus C2, see that's what we had right there, and then 3C1 plus C2 plus 5C3, it's right there, and then that one's the bottom left and that one's the bottom right. And so now that I have white out, watch this. Look at this. Come on. It's a new one, so I can waste it, and then I'll run out and I'll be like, what happened? I'll probably write the wrong thing here. So this is I think this was negative. Oh, look at that. C1. Okay. So that completes this problem. You know, you could use for matrices. Sometimes the book will do this. They'll use A, B, and C for C1, C2, C3. So you can use A, B, C instead of C1, C2, C3. This set, which is really, okay, so let me point this out. We're done with this problem. This is the span of S, has infinitely many creatures in it, whereas just S, which was this guy right here, just had it had 3 seeds in it. 1, 2, 3. Those are the 3 seeds. And we said that the last seed, well, we labeled it as dead weight, and we're going to come back to that in another section, but I do want to plant that word in your head for when we come back to it. Go ahead and do some more problems here. Problem number 8. So these are going to be a little different from the ones we've been doing. T is the subspace of R3 consisting of. Okay, so there's a subspace in R3. All solutions to this plane. So vectors that satisfy this plane. Find a set of vectors that spans T. So in the previous problems, we've been giving you the set of seeds. And some of those problems ask you to find the span of the seeds. Now they're giving you the subspace, which is the span of some seeds, and they're asking you to find the seeds. Find the set of vectors that spans T. Another way they could have said is they could have said find the spanning set of T. Okay, so T is the bigger set that has infinitely many vectors, and S is the set of seeds. So how am I going to do this? So they're asking us to do some of these problems backwards now. I'm going to take this plane here and I'm going to solve for any one of those 3 letters. Which letter would you solve for? Most of you would say Z, because you don't have to divide and get fractions. So that's what I'm going to do. Z equals 3x plus 2y. So that's what I did there. So this plane can be represented by these points. Watch this. X, comma, y, comma, and instead of putting a z, we're going to put 3x plus 2y. So this is the span of S. This is the plane, and we're trying to find the seeds. So this guy right here is the same as that. Now if I went like this, x, y, z, this represents any point in R3. But this is x, y, and then this is restricted, 3x plus 2y, so this is not any point in R3, it happens to be any point that's on this plane, or any vector that lies along this plane. So let's continue on this. What I want to do is I want to split this vector up into 2 vectors by addition. So on the first one, I just want to put the ones that have x's in them. So watch this. Here's x. The second coordinate does not have any x's, so I'm going to put a 0 there. And the third coordinate, we could put a 3x. Plus, and then this vector is going to hold all the y's. So look, there's no y there, so this is 0. And then y, and then 2y. It's probably easier to kind of go from here back to there. And so this step was called split. Okay, my next step that I want to do is I want to factor the x out of that first vector and factor the y out of that second vector. So when I do that, I have x, 1, 0, 3, plus, and then over here I'll factor out a y. Y, 0, 1, 2. So what I did in this step is I factored. Now a lot of you will want to just go there, because we're going to be doing these kinds of problems throughout linear algebra. When you do that, that's a split and factor all in the same step. So I've come up with a word called splatter. So when we do another problem, we will just splatter, because I think a lot of us had enough algebra where we can handle that. Imagine yourself going from here to here without the middle step, and some of you are like smiling, yeah, I could do that. Now, when we splatter, Look what we have here. This looks like something that starts with an L, and it's two words. This right here is a linear combination of two seeds. The two seeds being 1, 0, 3 and 0, 1, 2. Now what are they asking us to find? They're saying find the set of vectors that span T. Find the seeds. Look, any vector in this subspace on this plane, however you want to say that, can be written as a linear combination of those two seeds. So guess what? We have just found the set of seeds. We have found red, yellow, and here they are. Red. Some of you are like, just knock off the color analogy, Joe. I don't know what you're talking about when you say red. We found 1, 0, 3, and 0, 1, 2. There's our answer. And there's two elements in there, but there's infinitely many vectors on that plane. And so we can say that S spans T. It's not unique. So know that this answer is not unique. What if we had solved for X? Then you would have had something with Y and Z. You would have Y and Z and then an expression with Y's and Z's here. And then you would have got two different vectors when you splactor. But is that all right? Yeah, they're just two different vectors that if you take linear combinations of those, you get everything that's on the plane. So the answer is not unique. And sometimes your book, instead of giving you the plane, they'll just give you this, but instead of writing X and Y, they'll say like C1, C2, 3C1 plus 2C2. So the book might use C1s and C2s instead of X's and Y's on some of the problems. So know that. And know that it's not unique. Now there's one thing that I want to say, that when you're doing your homework problems, number 16 through 24, replace S with T. So I'll tell you why. Because we're first learning this. So anytime that I have a spanning set, the set of seeds, I always call that set of seeds S in this lecture. And then the span I call capital T. Well, your book, and other books would probably do the same thing, they just start calling anything in question S. So sometimes they'll call the set of seeds S, which I've been doing, and other times they'll say, let S be the subspace, and they'll call the subspace S and ask you to find the spanning set. So there's nothing wrong with that, except when you're first learning that, it can be a little confusing. So if you think you'll be confused by that, replace S, that's capital S, with capital T in those problems, and then it will be flowing just like I've been doing the problems here in the lecture. Let's go ahead and do a few more problems that are just like this problem, a little similar to this problem, where they give you the span and you have to find the set of seeds. Let T, see, your book would probably say S. Let T be the subspace of M3, that's 3 by 3 matrices with real numbers as entries. So you have a subspace of M3 consisting of all skew-symmetric matrices with zeros in the corners. Find a set of vectors that spans T. So what we want to do is we want to grab a general element from T, from that subspace of M3. A general element. So what do they tell us? They say skew-symmetric. That means zeros down the main diagonal. Now we can go back to the definition of skew-symmetric where it says A equals negative A transpose, but we'll just remember it this way. Skew-symmetric means that if I have an element here, I have the opposite element up there. Okay? So skew-symmetric zeros in the corners. So there's already zeros in those corners. I should put 0 here and a 0 here. I don't have to verify that this is a subspace. Remember, that was the last section. We're going to take their word on it, assume that they're being honest. So do I have the freedom to put any number here? And the answer is yes. So I'm going to put perhaps maybe an A there. Now I'm going to move down here. Do I have the freedom to put any number here? Well, once the A's there, because it has to be skew symmetric, I have to put a negative A there. Now this could have been a -7, and then down here that's a 7, and that's well represented right there. Now, do I have the freedom to put anything new here? I see on exams that sometimes people will then put an A here and a -A there, but you have the freedom to put whatever you want right there. So I'll put a B there. But once you do that, then you cannot put anything there. You have to put a -B there. So this 3x3 matrix represents any element that is in subspace T. Subspace T being skew symmetric matrices with zeros in the corners. We've captured them all. And the 0 vector, which is the 0 matrix, is part of that subspace. It should be. So what are we going to do? We're trying to find the set of seeds that generates all these guys. So what I would say to do is our new word, splactor. I'm going to go see if the camera is still running. Good, it is. So that would be bad to the camera will sometimes randomly stop. It does make a little beeping noise, but one time I didn't hear it and I just kept going, and here I was doing a lecture to myself that no one would ever see. That was bad. Okay, so how do I splactor this? I'm going to split and factor. So the first matrix is going to have an A outside, and I'm going to have 0, 1, 0, -1, and then the rest zeros, because the B's are going to be represented in the next matrix. So there's the first one, plus, and so now here's the one with the B's. So this is splitting. We split this into two matrices with matrix addition, and then we factor out the A, factor out the B. So this one's going to be row of zeros on the top, and then 0, 0, 1, 0, -1, 0. Okay, what does this look like on the right-hand side? This looks like a linear combination of two seeds. What are they asking us to do? Find the set of vectors that spans T? They're asking you to find the seeds. And so let's call that set of seeds, set S. We're going to list them right here. I know it's a little redundant, but we have to do it this way here. So 0, 1, 0, -1, 0, 0, 0, 0, 0. And the next one is the other one. Also, take note that last time we did this problem with the R3 as the vector space, we said that the solution to this, or the solution to that one, was not unique. The solution to this one is not unique as well, because we could have said, oh, we could have started here and said we can put anything here, and we'd put an A there, and then over here we'd put a -A. So this element could have had a 1 here and a -1 up there. So this is not unique as well. So that's how you do problems like this in your homework. I'm going to go ahead and do another one that is very similar to this. We're going to stick with M3, and we're going to pick a subspace of M3. See how that goes. Okay, let T be the subspace of M3 R, consisting of 3x3 matrices that such that the elements in each row sum to 0. Find a set of vectors that spans T. So let's go ahead and write out our representative matrix here. It says elements in each row sum to 0. So I am free to put anything in the first spot. I am free to put anything there. But over here, I'm sort of bound. I have to make sure the first row adds up to 0. So this is going to be negative A minus B. Each row will sum up to 0. Am I free to put anything here? Lots of times on exams, people will then put an A and a B and a negative A minus B. And that's true. It can be that, but it really can be anything. I mean, so you don't want to, the matrix can be like 1, 2, and then negative 3, and then 1, 2, negative 3. That does fit in that subspace, but we also have to allow for all possibilities. So CD, negative C minus D. EF, negative E minus F. So that is what the subspace looks like. It looks like that. And so what do we have to do? We're trying to find the seeds that generates anything in here. We're going to splatter. So A times the 3 by 3 matrix, 1, 0, negative 1, and then zeros everywhere else, plus, so this is going to be pretty long to write. Okay, so I wrote it all out. This right here is a linear combination of 6 seeds. So what do they want us to find? They want us to find the set of vectors that spans T. They want us to find the 6 seeds. So to find the 6 seeds, I'm going to go ahead and write my set like this. S equals, and then yeah, I'm going to write out all 6 of these matrices again. So I'm going to pause the video. Okay, there it is. I wrote it all down. I'll box my answer. So we found the set of vectors that spans T. We splattered, and I stopped time a few times so I can write it all out, because you probably didn't want to see me writing this out for 15 minutes. And that was quite an exaggeration. It was really only 12 minutes. Okay, I believe I wrote it all down correctly. I just took these seeds and put them in a list, and that's what they wanted. Let's go ahead and do another problem that's similar. I'll try not to do that much, but that was a lot of writing, and I didn't want to make awkward conversations as I was writing that down. Let T be a subspace of M3 consisting of all skew-symmetric upper triangular matrices. Okay, find a set of vectors that spans T. Let's see what this looks like. 3 by 3 matrices. So skew-symmetric. Main diagonal should be 0. Upper triangular means all the data is in the upper triangle, so that means the lower triangle is going to have zeros. But remember, it did say it was skew-symmetric, so whatever's here, the opposite of that number has to be there. So it looks like you're going to put the opposite of 0 is 0, the opposite of this 0 is 0, and the opposite of this 0 is 0. Wow. Find a set of vectors that spans T. Well, this is what T looks like. It's only one thing. Never had freedom. I never could put an A or a B down. So T looks like that, but so does its spanning set. Its spanning set is that. You take all linear combinations of that. Well, a linear combination of one vector is just a scalar times that one vector. You're just going to get that one vector. This right here is the answer. It was a lot easier to write the answer for number 11 than it was for number 10. Well, why don't we go ahead and do 2 more examples, and then we'll be done with 4.4. So 4.4 had quite a lengthy lecture here, Just a lot of stuff to learn. Find a spanning set for the null space of A. So you might want to pause the video and see if you can do this one on your own. Okay, so what do you have to do to A? You have to write out the augmented matrix. The augmented matrix looks like A and then you put zeros there. Well, now why are the zeros there? This is what we learned in the last section. The null space is the solution to A x equals 0, that homogeneous linear system. So what the majority of this problem is row operations. So I'm going to do those row operations for you. We're not going to spend a lot of time doing that. The first row is what you expect it's going to be. And then what I ended up getting is 0, 1, 1, negative 3, and a whole row of zeros. Okay. What happened? I did not put... okay, there it is. Good old whiteout. So there it is, and then we have that. Okay. So this right here, we'll call this X, we'll call this Y, Z, W. Where are my pivots? Or my leading ones? Right there and right there. X is bound. Y is bound. Z and W are free. W equals T. Okay, because he's free. Z equals S. The second equation here gives me that Y plus S minus 3T equals 0. So Y is going to equal negative S plus 3T. And then the last one, which is the first row, is X plus 0y minus 2z, so minus 2s plus w plus t equals 0. So this is just doing something from chapter 2 where we're solving a system, but we're going to do something new at the end. So we have x equals 2s minus t. I'm going to go ahead and write this up. Now remember, spanning set is the set of seeds. I'm going to write up this as a 4-tuple. So this is 2s minus t, comma, negative s plus 3t, comma, s, comma, t. So this is a plane in R4 if you care, but they want the set of seeds. That's what the spanning set is. So what am I going to do with this? I'm going to splactor it. So this is s times 2, comma, negative 1. So the negative 1 comes from there, comma, 1, comma, no s in the last coordinate, 0. Plus t, now I'm going to pick up the t coefficients. Negative 1, 3, 0, 1. Negative 1, 3, no t there, 0, and then 1. So look, this looks like a linear combination of 2 seeds. So our spanning set, which we've been calling S, is just going to be a list of those 2 seeds. So this is 2, negative 1, 1, 0. And then the other one is negative 1, 3, 0, 1. And so this spanning set generates the null space of this matrix. And right now it still seems abstract. You might be going, well, null space of a matrix, who cares? The math teacher cares. Or they don't and they're lying to you. But we're actually going to find applications. We will be looking at null spaces even when we're looking at differential equations. So it is a very important concept. It does seem like we're in la la land just doing some weird math, but you will see the applications, especially with the differential equations. Our last question is this one right here. Does S, which is those three vectors, span R3? Now, if there were just two vectors there, we would say, oh no, you would actually need more than two colors. You need like red, yellow, and blue. Okay, so before we answer that question, let's put this theorem up here. We've already done that. Okay, any three non-zero, non-coplanar vectors in R3 span R3. So when they say non-coplanar, that means they don't lie on the same plane. So if we can show that these do not lie on the same plane, then they span R3. Any two non-zero, non-collinear vectors in R2 span R2. But we're not doing that one now, we're doing this one. So remember that other theorem that we had where we were trying to figure out the volume of a parallelepiped, but it all came down to throwing these three vectors into a matrix, loading up the columns. And remember what we said, like if you go to take the determinant of that, and the determinant is non-zero, then these guys do not all lie in the same plane. So that is what we're going to do. Now, if the determinant is 0, then they all lie in the same plane, and the answer then would be no, they do not span R3. So, non-zero determinant? Yes. 0 determinant? No. After I'm finished with this, I'm going to actually show you why, and some of you may want to just skip over the why because maybe you don't care about that. So how do I take the determinant of this? I'm going to run across the first row. 1. 0, who cares? And then -2. Now 1 is in the positive position, so is -2. I'm just doing this determinant really quickly. And then I'm going to find the minor here, so this is going to be 1. And then over here, I'm going to find the minor on this one. It's going to be 4 minus 3, which is 1. So I have 1 minus 2, which gives me -1, which does not equal 0, which tells you these three vectors do not lie in the same plane. Okay, so these do not lie in the same plane, and because they don't lie in the same plane, if you do all linear combinations, you can reach anything in R3. So the answer is yes. Once again, if you had got 0 determinant, the answer would be no. So we're done with the problem, and some of you are a little unsatisfied. You're like, whoa, what's up with this? Let's pick the why. Why will this work? Okay, to see if those guys will span R3, let's find the span of them. C1, 1, 2, 3, plus C2, 0, 1, 2, plus C3, -2, 0, 1. So basically, now this is going to freak some of you out. Can you reach anywhere in R3? Okay. So, you know, you have three equations. They look like this. C1 minus 2C3 equals X. It's weird to have an X there. And then we have 2C1 plus C2 equals Y, because there's a 0 there. And then this one is 3C1 plus 2C2 doing the last coordinates, plus C3 equals Z. So the augmented matrix looks like this. I'm doing the columns 1, 2, 3, and then 0, 1, 2, and then negative 2, 0, 1. Here's X, Y, Z. And this is C1, C2, C3. What you need is a unique solution. You need a unique solution in order to get this, because if you had a unique solution, you would end up, okay, let's go the other way around. Okay. So we don't want to do our problems like this in the homework unless you're really like a math fanatic. Another way of saying we need a unique solution is we need this 3 by 3 matrix, the one that I circled, to be row equivalent to I3. Now why is that the case? Because if it was, you'd have like 1, 0, 0, 0, 1, 0. Okay, so if it was, it would look like this. There's a 1 there. And then you would have a linear combination of x, y, z. You'd have like x minus 2y plus 3z. And your equation then would say this. You would have C3 equals some linear combination of x, y, and z. I'm not saying that's the correct one for this one. And then C2 would equal some linear combination of x, y, and z. And C1 would equal some linear combination of x, y, and z. So you could always make it work. You can reach any point in R3. Now, if you had a 0 here instead of a 1, that's what I had originally written, then you would have had like x minus 2y plus 3z equals 0, which would be the equation of the plane, which would be what those guys would all lie on. So that you need it to be a you need this 3 by 3 matrix to row reduce to I3, which means you would want this 3 by 3 matrix, this guy right here, to be invertible. Invertible means the determinant is non-zero. And so that's why it works. That's why you could just take the determinant of these and see if you get non-zero, because we ended up getting a -1, which says those are invertible, which means this can be reduced to the identity, which means we're good to go. It means these three vectors do not lie in the same plane. Well, anyway, I think I rambled on enough about that. We are finished with 4.4. You guys have a good day, and I'll see you in the next video.